right, good morning and welcome back to microprocessor course. In today's class, we are going to learn about 8086 microprocessor instruction set. We know that instructions is a set of commands that a microprocessor can understand and execute. So we're gonna see different instructions that 8086 microprocessor can understand and execute. So before that, I'm gonna check if everybody is present in today's class. Class 5, number 1, number 2, number 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. Class 5, number 14. 15, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, class 6, number 1. Number 2, number 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, P21, 6, 15. Good. Class 6, 17. Name? Okay. All right, so in today's class, we are going to learn about the instruction set of 8086 microprocessor. We have seen that instruction set is a set of commands that a microprocessor can understand and execute. So we have 6 types of instruction that our microprocessor 8086 can execute. Data transfer instruction, arithmetic instruction, logic instruction, string manipulation operations, process control instruction, and control transfer instruction. Now, we're going to start with data transfer instruction. These are instructions that are used to transfer data, all addresses, into register, memory locations, all input-output ports. These generally involve 2 operands, source and the destination. They need to be the same size. Now, we have, for example, the syntax is for these data transfer instruction. We have a syntax opcode. We have destination operand, and we have the source operand. For example, we can move data from register EX data content of this 16 register will be moved to this 16-bit register. So they need to be the same size. They need to be the same size. Very important. So we have the source, which can be register or memory location or any immediate data. Destination is always a register or memory location. So the size should be either a byte or a word. We have the move instructions set for the opcode for data transfer instruction. Now, for example, here we move the content from a register A1 to the content in register 2. Or we can move the content from a register to a memory location. Or content which is stored at this memory location to a register. So this is what it does mean. We move the content from a register 1 into the register number 2. So this is the source of them, and this is the destination. We have the same. We can move a data, a 16-bit data, to a register. Or we can move a specific data to a memory location. Now we have exchange. For exchange of code, we are trying to exchange data. For example, we have exchange data from register 1 and exchange data from register number 2, which means after the execution of this instruction, the content of register number 2 will be in register number 1, and the content of register number 1 will be in register number 2. See, this is exchange data, the exchange content of these registers. Whereas here for the first instruction, which used the move, we are moving the content from a specific register to another register. Or the content of a memory location will be moved to a specific register. So the difference between these instructions, these opcode, is that for the first one, we are moving the content from a register or memory location to another location, either a memory or a register. For exchange, we are exchanging content. We may have a look here. For example, we may load the content in register accumulator register, for example. Then we load the content in register data accumulator register 6789H. Then if you move the content from register DX to AX, that means after the execution of this instruction, the content from register DX will be in AX. Now, you have to pay attention here to AX and DX. Once I do a single step execution, now you see our register, accumulator register, contain 1, 2, 5, 4, 5, because we just executed the first instruction. Then we're gonna execute the second one. The second one, after we executed the second one, this is the second instruction. We have TX, which now contains 6789. Now, after I executed this instruction, we found out that this data from DX will be in AX. Now, double check. We have instruction to be exchanged, that means the content from AX will be moved to TX, and the content from TX will be moved to AX. Now, after the execution of the first instruction, we have loaded this data into AX. Now we're gonna load the data into DX. Now we have found the data into DX. We have loaded the data into DX. Now we need to exchange this data from DX to AX, and the data into AX need to be into DX. Now you can find that now after exchange instruction, we have got the data from these two registers exchanged. All right, so now we are going to learn the next instruction, which is push. Now, push instruction puts data onto the stack. It has to put data onto the stack, and this will decrease the stack pointer, the SP, by 2. So, for a pop, it does have to remove data from a stack. Now, this SP will be increased, will be updated by 2. Now, we can push data, a 16-bit data, onto a stack. Our SP will be updated by decrementing by 2. Then we can calculate the physical memory pointed by the stack pointer by getting the stack segment is content, if you still remember from the previous class, times 16 plus the content of the stack pointer after it has been updated. Now we can get the physical location to which we have our stack segment pointed to. We can also push the content from the memory to onto a stack, and again we can calculate the physical memory address by using the segment, the stack segment content times 16. That is means to shift 4 bits on the left to get a 20-bit address plus the content of the stack pointer which has been updated because of the push instruction. Now, I can give you an example about the pop and the push instruction. Now, we can load this content into AX, and we have this content in our stack pointer. Then we need to execute the push instruction, which puts the data onto the stack. And we needed to find out how this stack pointer needs to be updated. Compile, then emulate. Now we have loaded the data into AX, and we have loaded the data into SP. We have loaded the data into SP as well, and AX. Now after the push instruction, we found out that the SP will be updated by decrementing its content by 2. Then we found that this will be 2456. 2454 because of the push instruction. Here we go. Now you found out that the content of the stack pointer has been updated by decrementing its content by 2. Now the in and and out instruction. The in instruction is to read a data from a register, from an input-output to a register. Now, we have to read, for example, a byte or a word from an input port into the register, AL register or AX register, depending on the content of the data. Out is to write a byte or a word from a register to a port. Now, you can understand that a takeaway for in and out instruction. In is to read a byte or a word from an input port into a register, whereas the out instruction is to write a byte or a word from a register to an input-output port. So which means these two instructions are opposite to each other. Now, you see we have in, we are going to read a word or a byte, in our case is a byte, from an input port. Now, we are going to read the content pointed by this port into AL. Because we have a byte, we have also lower byte order of our accumulator register. Same if you have a word, you need the accumulator register. Or you can also read a data into the accumulator register. That means this data, this is from an input port into a register, accumulator register in our case. So for out, we're gonna write a byte from an accumulator register to a specific port. Now, this is to write the data, a byte or a word. In our case, it's gonna be a byte or a word. Here is a word, 16 bits. We're gonna write a byte from input output. We're gonna write a byte from input output to a specific register. In our case, is a AF register. Or we can also write a 16 bit, that is a byte, to the lower byte accumulator register. Now, we're going to talk about arithmetic operations. Arithmetic operation, addition. Now, we can add the content of these two registers. For example, add register 1, register 2, register 1. That means we're going to add the content of register 2 to the content of register 1, and the result will be stored in the register 2. So this is the source and this is the destination. We add the content at this memory location to the content in the register number 2, and the result will be in this memory, in this register. Now, we can also add content from a specific register to the content into a memory location, then store the result at this memory location. We can also add a specific data to the content into the register and store the data into the register. We can also add the content, specific data, to the content at a specific memory location, then install the data at a specific memory location. We can also add 8-bit register to the content of low byte accumulator register and install the data at low byte accumulator register. Or a 16-bit register to the content of a 16-bit accumulator register and store the data at this specific accumulator. So we want to do each and everything now, but we're gonna do practicals during our practical session from week Now we can also add C means add the content of this register to the content of the register number 2 plus a carry from the previous operation. So when you are doing many operations, arithmetic operation, addition, there is a carry flag. When there is a carry in addition, that means that with ADC, addition with carry, the microprocessor will take into account the previous carry before it gets the final result of the addition. So the difference between these two addition arithmetic operations is that for add, it doesn't take any previous carry, but for add with carry, it will take into account previous carry. So this is really important. We have, for example, we can move AX, OX, OA, BC, and we can also move DX, OX, 1, 2, 0, 4. Then we can do add the content into register DX to the content into register AX, and the result will be in register accumulator register. Now, with ADC, it does do the addition as addition instruction, but it has to take into account the carry from the previous operation. So that's why we have different carries. We have different flags here. Carry flags. Now we see here we have different flags. That means that with add C, the instruction will take into account about the value that it will found here, okay, from the previous operation. Like we do when we are doing the addition and we have a carry, we needed to take into consideration the carry before we get the final result. That's why we have different flags. For example, this carry flag is very important when we are dealing with addition with carry. The next one, the next instruction is subtraction. We have subtraction. Sub is the opcode. We can get the content from register 2 minus the content in register 1, and the result will be stored in register number 2. Or we can subtract the content from a specific memory location to the content in register 1, then the result will be here, the result of the subtraction. Or we can also specifically use a specific data like an 8-bit data or a 16-bit data. So there we have the same syntax as for the addition. Next is sub with below. So when doing the subtraction operation, we all know that sometimes we need to below. So this sub B is subtraction with below. That means this instruction ensures that the below from the lower byte is subtract into the high word. So we have sub B, which means subtraction with below. That means this instruction will take into account to make sure that the below has been taken into account in the high word or high byte, depending on the length of the data that you are working on. We have increment or decrement. This means that we have increment the content in the register by 1. This is a register, an 8-bit register, lower byte or high byte. We need to increment this content by 2 and 1. This is very important when you are dealing with loops like loop for or loop y. Or do while. When you need to execute repeatedly instruction, you can use incrementation. Now, or decrementation. So we have also decrement, which allows the microprocessor to decrement the content in an 8-bit register or a 16-bit register, or the content which is stored at this specific memory location. Now, these are two important arithmetic instructions that allows the microprocessor to update the content of the register or the content at a specific memory location by adding its value to 1 or adding subtract its content by 1. So increment, decrement. Now, let's suppose we have move. What will be the answer of, what will be the content of AL after the execution of this instruction? Huh? Hello? We have to move the content FEH into AL. This is an 8-bit content into AL. Then we have increment. To increment the content in register LA, that is lower byte register by 1. What will be the result after the execution of this instruction? Huh? Huh? Hello? Answer my question. We have to load this content into AL register. Then we increment AL by 1. What is the answer? Huh? Then what is the answer? You are right. What is the answer here? Huh? The answer after this instruction is executed. What is the answer? You are right. What is the answer? Huh? Tell me. What is the answer? Class 5 number 3. Today's date is 3, right? Yes. Tell me the answer. We have to load this content in AL. This is FE. This means hexadecimal. Then we increment the content in AL. This is content by 1. What is the answer? Huh? If you are right, because we needed to add 1 at this content. Okay? So this plus 1, this FF. Okay? Now we can have multiplication, arithmetic operation, multiplication. We can multiply the content of AX register or DX register. Now you see here we have a single operand. Why? Because to make our hardware simple, we have only one operand here. So for example, you can have the content in accumulator register multiplied by the content in this register, or multiply the content in accumulator register by a content stored at a specific memory location. You can see we have 8x, okay? 8. No, that means that one operand is omitted, but it is for the purpose of making the hardware more simple. You see, if you have this content register here, 8, our microprocessor will know that the other operand is in the AM. If you have register 16, our microprocessor will know that the second operand is in AX. So this is the purpose of making our hardware simple. Same goes for a byte or a word data. You can have the content in accumulator register times a content, a 16-bit data stored at a specific memory location. Same goes for signed number. This is for unsigned number, and this is for signed number. You can have to multiply the content in lower byte accumulator register with a content, a 16-bit data. Then we store the result in accumulator register. Now, because here we may have a bigger length data, if you are trying to multiply a 16-bit data and a 16-bit data, we may have to store the data in two different accumulators, data register and accumulator register. Because the content might be longer, might be more than a word, so we need these two registers storing the content of the multiplication operation. The same, we're gonna also learn the division arithmetic operation. We have also one operand which is omitted. For example, if you have this content divided by a content, a 16-bit data divided by an 8-bit data, you have the quotient which is going to be stored in lower byte register. Or we can also use the modulo operation. If you do a 16-bit data mod a 8-bit data, remainder will be stored in high order accumulator register. What does it mean? Mod operation. What does it mean? Huh? What does it mean, mod? 5 mod 2 is 1. Why? This is the remainder. Yes, you are correct. So for a modulo, we write the remainder as the result of the operation. So the result of mod will also be stored in high order accumulator register. The same goes if you are dividing a 32-bit register by a 16-bit register. We have the content that will be stored in accumulator register, and so on and so forth for the modulo operation. We can have a 32-bit data mod a 16-bit data. So in remainder will be stored in data register. Now we can also have the comparison comparison operation when we have to compare the content in the register one to the content in the register number two, and we don't have to store the result for this arithmetic operation. Instead, it does modify the flags. So, for example, if we are trying to compare the content in the register 1 to the content in the register number 2, and we found out that the content in the register number 2 is greater to the content in the register number 1, we have the carry flag, the 0 flag, and the sign flag that needs to be set to 0. On the opposite, on the contrary, if we have the content in the register number 2, which is less than the content in register number 1, then the carry flag will be set to 1, 0 flag will be set to 0, and the sign flag will be set to 1. So, which means this comp operation does only modify the flags. We don't store the result of this arithmetic operation in any register in our microprocessor. Instead, it does only modify the content of the flags depending on the result of the operation. We can also compare the content stored at a specific memory location to the content in a specific register, and also if we have to modify the carry flag, 0 flag, or the sign flag. Now, we are going to talk about logical instructions. We have AND, OR, XOR. Now, tell me, we have A and B. A and B equals to 1 when A or B equals to 1 when A exclusive OR equals to 1 when. From your circuit course. Huh? You don't still remember? Class 6 number 3. Today's date is 3, right? Class 6 number 3. A and B. We have A and B equals to 1 when? When A equals to what? And B equals to what? And logic operation. The computer will do it for us, but we needed to have some basic, okay? So that you can say, okay, this is the result that I was expecting for. Okay, think about it. Class 5 number 6. 3 times 2 is 6. Class 6 number 6. Now, tell me, you think about the first question, and the class 5 number 6, think about the second question. Class 6 number 6, think about the third one. If you are done, tell me. In other words, so my question is this. you learned about this, yes or no? This is your first time to see this? No, tell me then. We have AND logic operation. A and B equals to 1 when? When all A and B equals to 1. Okay? Clear? Here is, okay, I change here. To be all. Tell me the answer. So this means A or B equals to 1 when A equals to 1 or B equals to 1. Okay? Now I change the question here, explicit or. Maybe this one is new, right? You don't know this one? This equals to 1 when? This is 1 or 0. Exclusive or. Here. So for exclusive or equals to 1 when A and B are different. So during the practicals, you have to do some exercise. You better have some basics because when you are doing some research, you can try to do it and find out if your result, the result that you were expecting for are the ones that you have got. So these are, for example, these are the basics that you need to have to understand these logic instruction for 8086 microprocessor. For example, we're gonna apply AND logic operation between the content in register 2 and the content in register number 1, and the result will be stored in register number 2. The same goes if you have the content which is stored at a specific memory location. You can try to apply the AND logic operation between the content at a specific register and the content stored in a specific memory location, or memory location register. So here we have the data, the 16-bit data or 8-bit data. Now, always remember that if you are applying the AND to the content in the register and a specific data, this data needs to be the same size as AF. That's why here we have if data 8. This means 8-bit data, okay? This means a 16-bit data because we have a 16-bit register. We have AND AL data 8. This means that we have an 8-bit data. We can also have AND AX data 16. This means that we have a 16-bit data. Okay, this is your 5-minute break. Take your break. We're gonna do some class after break.